All right, welcome to video 10. The topic of conversation now is going to be inverse trigonometric functions. So we have talked about now trig ratios from the unit circle, which allowed us to talk about trigonometrics as functions. We talked about the different representations, which was modeling, and we talked about how to solve basic trigonometric equations. So now we want to talk about how do I undo a trig function. So say, for example, we considered this equation, sine of x is equal to root 2 over 2. Now, if I'm considering solutions just on the one revolution of the unit circle, then we know that sine is going to be equal to root 2 over 2, specifically at pi over 4 and 3 pi over 4, that there's going to be two answers to this since there are two places where y can be positive on the unit circle. Now, when we talk about inverse trig and just inverse functions in general, remember that the whole idea of doing an inverse is to undo a function. And probably the best example that's very, very similar to how trig inverses work would be exponentials. So for example, if I had 2 to the x, and I wanted to undo this exponential, we would use logarithms to undo that, and it would be a log base 2. And so it's a little bit different from just when we were dealing with algebraic operations and doing the inverse, because we could easily undo them. Addition, you would just subtract, etc. But when I have something that's called a transcendental, so something that's like an exponential and something that's a logarithm, they take on two completely different looking functions since they're non-algebraic. And so a trigonometric function is of that same class. So again, it's a transcendental style function. And so when I want to undo the function, I'm literally going to undo it by taking the sine and applying the inverse to the other side. That inverse is notated by a -1 here just before the ratio. And so this expression right here, what this sign to the -1 represents, that -1 is not a power, but it stands for inverse sine. And some ways that we can also rewrite this, and this is an equivalent way, is to write it as arc sine. So anytime you see arc in front of a trig, that's also referring to inverse. It's a way to make sure that students and other people don't read this as a power. And we're going to see some stuff next week where we might deal with something that's like sine squared. And so in place of that -1 would be an actual power. And so that's why it can be really misleading, because that spot can either be a power, or if it's -1, it refers to the inverse, which is very different. So just be careful. For now, this -1, if I write that, means inverse. If I write arc sine, this means inverse. So now how do I actually calculate this? Well, we can't actually do it by hand right now. Instead, what I could actually use is my calculator to do this. So to get sine -1, you've probably used this before in geometry. You use this generally to find the angle in a right triangle. And that's exactly what I'm doing here, since x represents an angle. And so to get sine -1, if you're not familiar, you're going to hit the second button first, and then you're going to hit sine. This will put sine to the -1 into your calculator, and then you're going to type in root 2 over 2. Now, if your calculator is in radians, you should get the answer 0.785398164, but I'm going to leave it here. If you do it in degrees, you'll get 45, which would be a little bit easier to represent, because we know that 45 is pi over 4. And 0.785398 is pi over 4 if you were to actually put 3.14, etc. in for pi. And so this is giving me the same answer. But what I want you to really notice here is the discrepancy between what the calculator is providing me and the answers that we know I should get from the original problem. Right? Originally, we're starting with sine of x is equal to root 2 over 2. And when I apply the inverse, and when I go through and use this in terms of the calculator is only producing one of my answers, not both. So the question that we're going to try to investigate is, why is the calculator only producing this pi over 4 answer? Why is it not giving me this 3 pi over 4 as well? Like, why can it not output two different answers? It is a computer. It should be programmable to do that, right? So what's going on with that? And so that's what we're going to explore here in this next part. So the goal here is to essentially, again, figure out what's going on with inverse sine. So we're going to start with inverse sine, and then we'll look at inverse cosine and inverse tangent. All right, so I want to know about inverse sine, or sine to the -1. But before I can do that, this means I need to explore what the original function for sine is doing. So when I look at just sine of x, recall that sine of x has a domain from -infinity to infinity, and it has a range from -1 to 1. It's floor to ceiling. There's no vertical asymptotes, there's no breaks, but I have this. Now, when I go through and I want to find the inverse, f to the -1, and I'll put arc sine here, recall that when we do inverses, we are literally inverting my input and output. So the domain, when it comes to inverse sine or arc sine, is the range of the original function. So my domain now is going to be -1 to 1, and my range would show up as -infinity to infinity. But there's a problem with this, and it involves looking at what the graph of the original function sine does. So I'm going to pull Desmos up, and I'm going to go in, I'm going to add pi's in so we can see this in terms of radians. I'll hit projector mode, and then I'm going to zoom in a little bit since we're just dealing with the basic graph. All right, so let me put in sine x. All right, now here's the basic graph of sine, right? And we know that this graph will go on and on and on infinitely because its domain is all the way to -infinity on the left-hand side and all the way to positive infinity on the right-hand side. Well, think back to the previous mod, so mod 4. All right, when we talked about how can a function have an inverse when it does not pass the horizontal line test. For example, if I go through and I plug in y is equal to 0.5, notice how many times that horizontal crosses the original function. And so if you remember, if a function does not pass the horizontal line test, its inverse cannot pass the vertical line test because it swaps the x's and the y's. So just to sketch this, because I don't think I can get it to be sketched in Desmos, remember that if my original function is doing this, and I was to swap the x's and y's, that means the inverse graph would do something like this. It would be a wave flipped vertically. And if I'm looking for this inverse to be a function, this would never pass the vertical line test. So what we talked about in mod 4 was, in order to make the inverse a function and pass the vertical line test, I need to restrict the domain of the original function. And I need to restrict it so that the original function will pass the horizontal line test. All right, so I'm going to go back into Desmos. And so in other words, when I look at this graph here, I want to pick the smallest possible integer, or not the smallest, but I guess the largest possible domain, so that this graph will pass the horizontal line test, so that this blue line here will only hit the graph once. Now, there are multiple ways that you could essentially do this, but the theory is that if I restrict it based off of a min to a max, and I cut it off here at these two values, then I'm only going to hit this graph once, because I'm only going up to the max and I'm not coming back down, and I'm only going down to the min and I'm not going any further back up. So there's no overlapping, there's no parabolas. Now in Desmos, to help illustrate that, what I'm going to do is put in essentially the good old sideways mustache, and then I'm going to tell it I'm only going to go from this min, so -pi/2, so -pi/2 is less than or equal to x, which is less than or equal to +pi/2. So notice with this restriction now, looking at just this piece of the original sine, And let me put in that original sign so you can see what the original function was doing again. So here's the original. Here's that little sliver, so you can see that just that little piece of it. If I put this horizontal back in, notice that as I scan through, for the red, I'm only going to hit it once, but for the green, I'm hitting it infinitely many times. So once I take away, and I'm only focusing on one min to a max, I'm only hitting the graph once. And therefore, this part of sine now has an inverse that is a function. And so I need to go into what we wrote here, and I'm going to change what we wrote for the domain because I restricted it from negative infinity to infinity down to negative pi over 2 to positive pi over 2. This means for my inverse, my range has now been restricted to negative pi over 2 to positive pi over 2. And so what this ultimately is telling me is that when I'm plugging in these values for arc sine, my answers will only come out, or my outcomes will only show answers in between negative pi over 2 and positive pi over 2. So what does that mean visually? All right, so if I go to my unit circle, and I'm just going to kind of draw a basic unit circle here. If I'm starting here at 0, if I want to go to positive pi over 2, I'm rotating just 90 degrees in the positive direction, but I'm stopping here because that is where pi over 2 is. I can't go past it. If I'm starting at 0 and I want to go to negative pi over 2, I would be rotating clockwise 90 degrees, and negative pi over 2 would be here, but I can't go past it. So notice in terms of the circle, I'm not getting any answers over here in quadrants 3 or quadrant 2 or quadrant 3. Inverse can only give me answers that exist here in quadrant 1 and here in quadrant 4. But the tricky part is that my angles in quadrant 4 aren't the angles that you see in the unit circle, but they're the negative coterminals for those that are in the quadrant 4 on the unit circle. So for example, if again I'm starting here at 0 and I'm rotating this way, the first special angle that I would hit would be negative pi over 6, not 11 pi over 6. The next one would be negative pi over 4. The next one would be negative pi over 3. Because I'm starting at 0 and going clockwise, I'm not able to go counterclockwise to get over here. So I can't ever get past pi, I can't get to 3 pi over 2, etc. when I'm dealing with inverse sine. Now, if I'm going in terms of the positive direction, this means my answers are going to be anything from pi over 6, pi over 4, pi over 3, and pi over 2 like we would normally see. So see how this is restricting me now to, if I'm doing inverse sine of something positive, that means my answers are going to be only come from the first quadrant. And if I do inverse sine of something negative, I'm only going to get an answer from the fourth quadrant here. So for example, let's say I wanted you to find inverse sine, so I'll write it this way, inverse sine of, say, radical 3 over 2. And I want to know what this is equal to. Well, what this is essentially asking you is it's saying sine of what angle will give me root 3 over 2. But that what angle has to be in between negative pi over 2 and positive pi over 2 because of the restriction of my range for inverse. And so if I'm looking at this unit circle that I drew, and I'm comparing and saying, okay, where is there a y-coordinate of positive root 3 over 2? This would have happened here at pi over 3, and that's the only answer that I would get when I'm doing inverse sine. This is why the calculator can only produce pi over 4 and not 3 pi over 4 as a solution, because 3 pi over 4 is over here in quadrant 2, and inverse can't get there. Again, it stops, it's blocked here at pi over 2. It doesn't exist past that line. So it's never going to give me any answers past that line. All right, and so this is inverse sine. This is arc sine. I'm going to give you some more examples of this in the next part because I want to talk about inverse cosine, and I want to look at it very, very similarly. So if we wanted to do cosine, but I want to talk about its inverse. Well, the original domain is like sine. It's negative infinity to infinity. And its range, like sine, is -1 to 1. Well, this means for the inverse, these two are swapped. So the domain right now for my inverse would be from -1 to 1, meaning I can only take the inverse cosine of values in between that. And then my answers have to be right now from negative infinity to infinity. But just like sine, there's an issue with this because going from negative infinity to infinity, I would not pass the horizontal line test. Cosine and sine are the exact same graphs, right? Cosine has just been shifted. So just like what we did with sine, I need to restrict the domain for cosine, and I'm going to restrict it in such a way that I'm not only using smaller values for my angles, but it's going to be essentially around 0, kind of like what we did with sine. So I'm going to go back into Desmos. Let's delete that. I'll leave the horizontal. We'll delete that. Okay, and so I'm going to put in cosine of x. So you can see again cosine and how it's going to not pass the horizontal line test. So right now, if we were to do its inverse would not be a function. I have to restrict the domain. Well, just like what we did with sine, we're going to restrict it to where we go from one max to a min. Because as long as I cut and I erase everything else, then I'm going to work in terms of the horizontal line test, right? I can't go past a max and I can't go past a min. I have to restrict it according to those two values. Well, those values would be 0 and pi. So I'm going to type in a new cosine like we did before just to kind of justify this. I forgot to put my x in. All right, let me get my sideways mustache. All right, and so this time we're going to go from 0 to pi. So you can see by this black line here, this is the sliver that we're looking at. And notice that this is that one little piece from one max to a min. Now, you could look at this and say, okay, once I take away the original graph, now this is a function in terms, or its inverse would now be a function. And so this is the restriction that I'm going to use. Now, one thing that I want to point out is that what if instead of going from my first max to my first min, could we not restrict it in terms of going from my first min to my next max? Could we do pi to 2 pi? And the answer to that is yes, right? Because if I set that restriction, then this would create a pass in terms of the horizontal line test. It means the inverse would now be a function. The problem is that we're looking from pi to 2 pi, and it's not the first interval that works. And so standardized, or remember, kind of standardizing things is really, really important. And so instead of anybody being allowed to pick their answers, standard was, well, let's always kind of center at 0 and then choose the first interval that works. In particular, any intervals that would be positive. And that's why we choose 0 to pi and why we don't worry about any of the other ones. And this was the same argument in terms of sine. All right, so going back into my notability in our video here, I'm restricting the domain, but unlike sine, I'm restricting it from 0 to pi, which means the range of outcomes for inverse cosine would be from 0 to pi. So this is a little bit different. So again, like what does this mean visually? So if I go to my unit circle and I'm doing inverse cosine, notice that I'm getting answers from 0, but they're ranging to pi here. So I'm getting all of the answers that are in the first quadrant, and I'm getting answers in the second quadrant. But this wall stops at pi. I'm never getting down here in terms of the third and fourth quadrants. So there's no way that inverse cosine can ever produce an answer that's more than pi. It's only going to give me answers of things like pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, and 5 pi over 6. These are the only answers in terms of the special angles that you would see when calculating anything that has an inverse cosine. So just as an example, if I was to do inverse cosine and I wanted you to evaluate this, and I said do inverse cosine of something like negative 1/2. Well, what this is looking for is really cosine of what would be negative 1/2, but that what has a very, very specific restriction that it can only come from 0 to pi. My answer has to exist in either the first quadrant in the unit circle or the second quadrant. Well, because this is the x coordinate and it's negative, I know my answer has to come from the second quadrant, and this would occur specifically at 2 pi over 3. And so this solution here would be 2 pi over 3 and only 2 pi over 3. There are no other solutions because I can't get down here to the quadrant 3 where that other solution could possibly exist. The only other correlation before we do inverse tan that I could really think about that hopefully will make this methodology and these ideas make sense would be the difference between these two equations when solving. X squared is equal to 4 versus x is equal to the square root of 4. Now here, when I'm solving x squared is equal to 4, notice how you would have to introduce the square root. But by introducing the square root, we have to take into account the two different answers, positive 2 and negative 2, because both of these answers would work in the original equation, right? Negative 2 times negative 2 would be equal to 4. 2 times 2 would be equal to 4. Therefore, I get two solutions. Much like if I was solving the initial problem, sine of x is equal to, say, root 2 over 2. This gave me pi over 4 and 3 pi over 4, because in both of these spots, sine is specifically root 2 over 2. But think about if I have and I start with the square root, there is no introduction of it into the problem, then the square root of 4 is just 2, right? This doesn't include positive and negative. This is only the principal square root. It's only the square root of 4. So that means there's only one solution. And this is directly corresponding to if you started with inverse sine in your problem, then there can only be one solution because of how inverse sine is defined to start with. The answer could only be pi over 4, and that's it. So when you have to introduce inverse sine into a problem to solve, there can be two answers because of how the original problem is written. But if you start with inverse, there is only ever one. We're never counting any of the other solutions. Okay, so hopefully that kind of helped. Let's take a look at inverse tangent before we take a look at some more examples that I've got down here. So for inverse tan, so I meant to label this. So this is inverse cosine, inverse tan. Okay, now tangent is kind of unique. We looked at this in the video on Monday. Tangent has a domain that runs from negative pi over 2 to positive pi over 2. Well, sorry, hold on, I lied. It has a domain of anything, right? But those vertical asymptotes which occur at every pi over 2. So it has this definition. Its range is all real numbers. There is no limit to how high or how low a tangent graph can go. So when I look at the graph for tangent and I want to do its inverse, so let's go through and let's type this in here. So tangent of x. When I zoom out here, notice that for this to pass the horizontal line test, I would only need to take one of these bands. Well, the one band that I'm going to use would be the one centered around 0. And if my vertical asymptotes are at pi over 2 and negative pi over 2, then that's going to be my restriction. In other words, I'm going to go through and set this restriction to only be this first band in the middle that I kind of have highlighted. And so to do that, we're going to do negative pi over 2 to positive pi over 2. So now when I look at this graph as a whole, this graph will always pass the horizontal line test, meaning its inverse will always pass the vertical line test. And I want to show you kind of what this one looks like, and I'll do it after we kind of define it. So, oh, hold on, I'm getting ahead of myself. So let's go back to here. So I'm going to change my restriction, and this is what I was actually putting in to start with, is that because of the vertical asymptotes, we're going to take the function to be those in between those first vertical asymptotes. So the domain is going to be parentheses negative pi over 2 to positive pi over 2. And it's parentheses because these are asymptotes. I can't actually use these values. So notice how similar this is to sine, that it's the same boundary, it's the same restrictions, but sine I could use pi over 2 and negative pi over 2, but tangent I can't because this would create a division by 0. So this means when I do my inverse tan, my arctan, the domain, what I'm allowed to take the inverse tan of, is anything. There is no issue with taking inverse tan of something greater than 1 or less than negative 1. But my range, the outcomes that I could get, my answers, have to be in between, but do not include negative pi over 2 and positive pi over 2. So in terms of the unit circle, this would have the exact same answers as inverse sine. They would only exist in the first or fourth quadrant, specifically 0, pi over 6, pi over 4, pi over 3, but never get to pi over 2. So I'm just going to put an open circle there. Down here, this would be negative pi over 6, negative pi over 4, and negative pi over 3, and then never get to negative pi over 2. So my answers can stem from here and here. So say I was going to evaluate inverse tan of negative 1, and I want to know what is this equal to. What this is essentially asking you is tangent of what is equal to negative 1, but that what has to be specifically in between negative pi over 2 and positive pi over 2. Well, because it's negative, I know my answer has to come from the fourth quadrant because everything is positive in the first. And anytime you have tangent equal to 1, that means I'm looking at my over 4s because it's the only place where I have an x and a y coordinate that are the same and can actually produce 1 when I set up their division. And so this answer would directly be negative pi over 4. All right, now I told you earlier, and I don't know if you've kind of noticed, we've pretty much defined essentially 3 new functions. We have inverse tan, we have inverse cosine, and I have inverse sine. That means each of these have their own domain, their own range, and their own graphs. Now, I didn't really graph arcsine and arccosine, arcsine and arccosine. I didn't really graph them at all. And it's really because their graphs are not used very often. And I mean like very, very slim to none. The only inverse graph that you will actually see, and this will be if you pursue a major or a field of study that involves calculus and Cal 2 and Cal 3, etc., is arctan. So I want to show you what the graph of arctan looks like, again, just so you can kind of get a visual for it, but you're not going to be evaluated or assessed on specifically the graph of arctan. So I just want to give you that heads up. Okay, so if you were looking at the graph of tangent that we've got restricted, imagine that we were to flip this along the main diagonal, again, swapping all of the x's and y's. So if I was to mirror this, then I would expect this to look almost like an S. So I'm going to put in inverse tan. So let's see, functions, inverse tan of x. So here's the graph of inverse tan. Now there's something interesting that happens here, and this is why you see this sometimes in calculus, is that it looks like the graph will continue to rise and continue to fall infinitely, almost like a cube root graph. But as I zoom out, I actually do not. In other words, the graph starts flattening out and flattening out, and it never actually gets past 2 values, specifically the horizontal line of pi over 2, and it never falls below negative pi over 2. Well, why is that? Well, it's due to the restrictions that we chose for tangent, right? Remember, my restrictions were x is negative pi over 2 to pi over 2. So when I do its inverse, this is going to restrict my y values, right? It fixes my floor and ceiling. So now, when I'm looking at this function, my domain can be all real numbers, but I'm stuck in between these two boundaries. I can never go higher than them, so you see it fixed. And so when you talk about limits in calculus, this is something that's really, really important. Because a limit is that it's a boundary. Like, what are you getting closer and closer to, but never actually reach? What can you not get past? Where is your fence line? Well, in this case, that limitation is pi over 2. The function will never be pi over 2, but that's my boundary because I can never get past it or even to it exactly. But I can get as close as I want to it, which is kind of weird to think about. All right, and so this is arctan. This is its graph here. An important one to just be familiar with, but one that you're not going to have to know for this class specifically. It's kind of outside the scope of what we really kind of care to do. Okay, so let's take a look at some inverse trig problems. We're going to be evaluating and using specifically the unit circle and using what I've sketched so far to kind of help us. So here is the example. So I want to evaluate inverse sine of root 2 over 2, inverse cosine of negative 1/2, inverse tan of 1, inverse tan of negative root 3 over 2, inverse cosine of positive root 3 over 2, inverse tan of negative root 3 over 3. All right, so let's look at the first one. Now, we've actually already done this one, so let's mix it up a little bit. I think I'm going to make it negative instead and really throw you for a loop for this one. All right, so this problem here, it's essentially saying, all right, I want to look for the angle, specifically an angle that when I take the sine of it, I would get negative root 2 over 2. But that angle that I'm doing has to be in between negative pi over 2 and positive pi over 2. Well, where is sine going to be negative? Well, that's going to occur in quadrant 4. So just to draw a little basic circle right here, it occurs here. And this corresponds to negative pi over 4, and that's my answer. Excuse me. All right, looking at inverse cosine of negative 1/2. Now, this one we also did earlier, so I'm going to take off the negative here. Let's look at just inverse cosine of 1/2. Okay, so this is looking for, again, an angle, but specifically, I'm looking for where is cosine equal to positive 1/2, but that x has to be in between 0 and pi. So I'm only going to get one answer from here. Looking at the semicircle that I drew earlier, this is going to happen in the first quadrant, specifically at pi over 3. And that's my answer. There are no other solutions. All right, let's look at inverse tan. So where is inverse tan equal to, what is inverse tan of 1? In other words, tan of what is equal to 1? But specifically, again, this has to sit in between negative pi over 2 to positive pi over 2. This would give me an angle of pi over 4. Like we talked about earlier, the only place the tangent can be 1 is when my x and y coordinate is exactly the same. And here I want it to also be positive. That means it has to occur in quadrant 1. All right, inverse sine of negative root 3 over 2. Well, this is essentially saying sine of what is equal to negative root 3 over 2. But again, my answer has to come in between negative pi over 2 to positive pi over 2. So where does that happen? Well, I'm looking for negative root 3 over 2. So this will be in quadrant 4. And this will specifically happen at an over 3. So in this problem, negative pi over 3. That's my answer. Cosine, inverse cosine of positive root 3 over 2. This is asking where is cosine equal to positive root 3 over 2, but that where has to be in between 0 and pi. So positive root 3 over 2, this would be in the first quadrant, specifically at an angle of pi over 6. All right, now this one's going to be a little bit trickier. So inverse tan of negative root 3 over 3. This is essentially saying tangent of what is going to give me negative root 3 over 3. Now, I'm going to unrationalize this to kind of help us out. In other words, this one actually came from -1 over root 3. And this is just going to take some practice and getting used to it. And as you do more and more problems, you'll get used to this pattern. Otherwise, what you would need to do is go through and figure out which ordered pair, when you do y over x, would give you radical 3 over 3 when you rationalize. Now, by unrationalizing this and getting this radical 3 back to the denominator, it kind of helps tell me that this one was 1/2 over 1 over root 3 over 2, where the 2's had canceled out, meaning that my radical 3 needs to be in the x-coordinate, and my 1 needs to be found in the y-coordinate. So this would occur at the over 6's. And again, because I want tangent to be negative, and this angle has to be in between negative pi over 2 and positive pi over 2, I know this would happen at negative pi over 6. And that would be my final. So this is how we evaluate. Now notice on all of these problems here, we started with the inverse trig, meaning that I can only get one solution out of this. Now you can check all of these answers in your calculator. The tricky part is in using your calculator, because I'm looking for these answers to be radians, I need the exact answer. Your calculator won't give you the exact value. Most calculators will essentially go through and use 3.14 for pi, and so you're going to see the decimal like we saw at the very beginning. So you just need to be careful when you're going through and solving these problems that way because of that. All right, now, how would this actually be used, right? And where is this essentially going to be useful? Now, you saw applications of inverse when we were doing it in terms of a right triangles in geometry and trying to solve for angles if I know some sides of the triangle. Well, the harder types of questions would look something like this. All right, consider cosine of x is equal to 0.3. And I want to consider this, though, for all of my x's from 0 to 2 pi. So x is a radian measure. Now, 0.3 is not on the unit circle, meaning that my x's here, my solutions, are not exact values. They're not special angles, meaning I can't just look at the unit circle to solve. So then how in the world do I solve a problem like this for x? Well, the only way is to use a calculator. So I'm going to go through and do inverse cosine of 0.3, but again, my calculator needs to be in radians, so make sure you have that set up. Do not use degrees. So in the calculator, I'm going to do inverse cosine of 0.3. Let me get my calculator up. Okay, so inverse cosine of 0.3. I get 1.2, so x will be approximately 1.27 radians. Now, remember that this is only giving me my one solution, specifically the solution that keeps me in the first quadrant, because inverse cosine can only put out one answer. But how many answers do I have in the unit circle when I'm solving initially for cosine of 0.3? There should be 2, right? And then drawing a circle, just as a reminder, cosine is positive here in quadrant 1 and positive here in quadrant 4. So this 1.27 is the first answer, right? It's an answer that's roughly about right here. So this angle right here represents 1.27. Now my second solution would be going all the way around and finding the mirror image to that. So I need to figure out how to find it. Now, what's really, really helpful is regardless of it being positive or negative in a calculator, we'll see this in the next example, and I'll kind of prove this point in the next example. What we just found right here is the reference angle. That's what this 1.27 is. If you notice, it is the angle in the first quadrant, so therefore I can treat it as my reference, because if this angle that gets me down to the fourth quadrant has the same cosine value, that means it must have the same triangle and the same reference. So it must mean that this is also 1.27. So how could I figure out then what this blue line is? How can I figure out this other angle? Well, if I think about it, notice that theta plus this 1.27 would create a full circle, which is 2 pi. So in order to find my second possible solution, and here I'll kind of put this back in terms of x, I just need to subtract 1.27 from 2 pi. And so this is going to give me approximately 5.01 when I round to the second decimal place. So here are my two solutions to the original problem of cosine of x is equal to 0.3, right? Cosine of what angles will give me 0.3? To check this, we could plug this in. So again, make sure your calculator is in radians. So if I do cosine of 1.27, I get 0.2962, which is approximately 0.3. If I do cosine of 5.01, I get approximately 0.293, which again is approximately 0.3. So it means both of these angles work. Both are in between 0 and 2 pi, which is 6.28, which means that both are solutions to the original problem of cosine of x is equal to 0.3. All right, well, let's take a look. I've got one more final example to look at here. So what if I have sine of x is equal to 0.3? And I want to go through and solve this problem. Specifically, I want to find all angles from 0 to 2 pi, where if I was to plug them in, sine would give me 0.3 as a solution, like what we just did for cosine. Well, to solve this, I need to do the inverse sine. I want to isolate the x, so that means I need to get rid of sine. Well, how do I undo a function? We have to take its inverse. So I do x is equal to inverse sine of 0.3. Well, I have to do this in a calculator because 0.3 is not a special angle. And when I do, I'm only going to get an answer that's either in the first quadrant or the fourth quadrant. In this case, I'll get an answer that puts me in the first quadrant. And by doing inverse sine of 0.3 in radians, this comes out to be 0.305. I'll go to 3 decimal places. So this is my answer. Now, because this is my angle in quadrant 1, this is also telling me the reference for any other quadrant. So that means if I was to look at a unit circle and I wanted to know where could sine be equal to 0.3, it would occur here in the first quadrant and here in the second quadrant. I specifically know now the first quadrant answer. I know that this one has to be 0.305. I want to try and figure out what its mirror image is over here in quadrant 2, which I know now, because that's its reference, this angle is also 0.305. I need to know what the overall angle to get there is, looking at it in terms of being in standard position. Well, I need to establish, well, what's a relationship between this and my reference here? Well, notice that that angle, which I'll call x, plus my reference of 0.305 must be equal to pi, because that would make one straight line. So now I can go through and solve for x by doing pi minus 0.305, which would be approximately, let's see, pi minus 0.305, I get 2.84. Now we could check this by going to our calculator again, putting it in radians. I can do sine of 0.305, and I would get 0.300. If I do sine of 2.84, I get approximately 2.297, which is 0.30. So both solutions are in between 0 and 2 pi, which means both solutions are ones that I have to include. Now, these are two fairly straightforward examples for calculating inverse sine and inverse cosine when we're looking at things that are not on the unit circle. These can get a little bit harder. I'm going to give you some of these and challenge you in terms of the practice. So make sure you take a look at the practice problems. And then as we get into more solving questions when we're verifying and doing things like that, I will also give you some more examples that are, again, a little bit harder in terms of doing the inverses. and simplifying some expressions with this idea. So at this point, let me know if you have any questions. Feel free to shoot me an email as we're getting to the end of this mod. And definitely take a look at the practice problems for this lesson because it's going to include some problems that I didn't show you here that I do want you to try and attempt. All right, so again, I hope you have a good rest of your day, and thanks for watching.